Many reinforcement learning algorithms exist, ranging from simple methods to highly sophisticated ones. In this video, I'll explain the foundational algorithms that everyone interested in reinforcement learning should understand. Reinforcement learning approaches track the interactions between an agent and an environment. The agent can see some information about the environment state. This can represent a variety of different scenarios, from the current screen at a game to the inventory of a factory. The agent uses that information to take actions that modify the environment. The actions can be the movement of a robot arm or change a parameter in a simulation. The environment responds with a reward signal that indicates how desirable the outcome of the agent's action was. The agent's objective is to maximize the sum of future rewards accumulated from a given point onward, not just the immediate reward. This cumulative sum of rewards is the return G. This sum is often discounted so that rewards received sooner are more valued than rewards received later. In this equation, gamma is the discount factor which determines how much the agent values future rewards compared to immediate ones. If the discount factor is close to 1, the agent thinks long-term. If it is closer to 0, the agent will focus on short-term gains. This mimics human behavior, as we tend to value shorter-term gains more than longer-term ones. In many cases, the agent-environment interaction is repeated until a terminal state is reached. The sequence of interactions from a starting state until a terminal state is called an episode. Not all types of problems have episodes. For example, if you're working with an agent that controls the temperature of a room, this agent will take actions continuously. For this reason, this is called a continuing task instead of an episodic task. In both episodic and continuing problems, the history of states, actions, and rewards as time passes is known as the trajectory. The trajectory information describes the interactions between the agent and the environment, which can be used to build a policy. The policy tells the agent what action it should take in each state. Formally, a policy is a function that maps states to probabilities of selecting each possible action. To assess how good it is to follow a given policy, we can use the value function to calculate the utility of a given state. This is known as the prediction problem. But in the case that we want to find the optimal policy, which is known as the control problem, we must estimate the returns obtained when an agent takes an action in a given state. So in this case, we must use the action value function. To find the optimal policy, the simplest algorithms build a table that contains the estimated return associated with taking an action in a given state. Once we have estimates of the action value function, we can build a policy. The simplest policy always selects the action with the highest estimated value function. This is the greedy approach. There's a problem with this approach. Imagine that to start your training process, you initialize all the values in the queue table to 0, and in the first interaction with the environment, you're in state 2, select action 3, and receive a large reward. You will update the estimate of the action value function by a large number. Therefore, next time you are in state 2, you select action 3 again. And this will be repeated indefinitely unless your estimate of Q for that action becomes negative. However, you have no reason to believe that the other actions would give you a smaller reward, as those actions haven't been tested yet. This is the trade-off between exploiting known rewards and exploring potentially better actions. To address this issue, we often use an epsilon greedy policy, in which most of the time the agent chooses the greedy action, and with a small probability epsilon, it selects a random action instead. This simple exploration strategy allows us to successfully train the algorithms we'll discuss throughout the rest of the video. To train the reinforcement learning agent and obtain a policy, we will follow the generalized policy iteration, where we keep both an estimate of the action value function and an approximate policy. The estimate of Q is repeatedly updated to approximate the action value function for the current policy, and the policy is repeatedly improved with respect to the current Q. In theory, this iteration between policy evaluation with policy improvement leads to convergence to the optimal policy and its action value function. In practice, however, the quality of a sequence of generated policies may vary, and if the policy evaluation step is incomplete, the quote-unquote improved policy may be worse than the previous one, making the iteration we see on the screen diverge from the optimal solution. To avoid decreases in policy performance, it's common to store the sequence of policies obtained, and when learning is over, measure the performance of these policies by running some tests. Then the best policy can be selected. The implementation of this idea for the simple tabular algorithms requires us to initialize the action value function and then run many episodes of experience to update our estimate of Q. At the beginning of each episode, the environment is reset and returns an initial state. Then, at each step, the agent chooses an action according to its current policy. The environment responds by returning three important pieces of information: the next state, the reward received, and whether the episode has ended. At this point, the learning algorithm updates its estimate of Q using the newly observed experience. This update step is the main difference between the algorithms we'll study, but regardless of the specific update rule, the surrounding structure remains mostly the same. Recall that the action value function is the expected value of the return. So if we had multiple records of G for each state and action pair, the average of those estimates should converge to the true value of Q, according to the law of large numbers. But that requires us to keep track of all returns encountered by all state and action pairs. To avoid storing all of those values in memory, we can compute the new average value using the previous average and the latest return calculated. But this requires us to keep track of the number of times each state-action pair appeared in all of the episodes we played. So it's common to modify this approach to multiplying the second term in the right-hand side of the equation by a small constant instead of the number of counts. This constant is known as the learning rate. The idea is that you update your estimate of Q by moving the current estimate a little bit towards the latest value of return obtained for that state and action pair. The easiest way to combine the returns for each state and action pair is to play the entire episode, then retroactively calculate the returns obtained after visits to each state and action pair. This requires us to keep track of the states, actions, and rewards at every step of the episode, known as the trajectory. This is the approach taken by the Monte Carlo algorithm, and to implement it, we start with the standard training structure we already talked about. But this time, we keep track of the trajectory for each episode. Then, at the end of the episode, we loop backwards through the trajectory to calculate the return associated with the state and action pair, and use it to update our estimate of Q. Note how this update, which is the learning step in reinforcement learning, is only performed after the episode ends. This delays convergence to an optimal policy, and it also means that Monte Carlo cannot be used with continuing tasks. Additionally, note that the algorithm shown here has linear time and space complexity with the length of the episodes due to storing the trajectory for all time steps. This can impose large memory requirements. This limitation is addressed using the temporal difference method, which updates the estimate of the value function at the current state by moving it closer to the reward obtained plus the discounted expected reward at the next state, which serves as a proxy for the remaining rewards. The term at the right-hand side of this equation is known as the TD error because it measures the difference or error between the current estimated value of ST and the better estimate calculated by R plus gamma V, which is known as the target of the update. Note that in this algorithm, an estimate of the value function at st plus 1 is used to estimate the estimate of the value function at st. Because of this, we say this algorithm uses bootstrapping. The use of the value function in this method means that it can only estimate the value of a given state when a policy is already defined. The control version of this algorithm learns the action value function instead, which allows us to obtain the policy using generalized policy iteration. To implement this version, we need to keep track of the current state and action, the reward obtained, and the next state and action. For this reason, this algorithm is called SARSA, and it can be implemented with little modification to the standard RL training structure. The idea is just to evaluate the next action to be taken and use the current and next states and action pairs, along with the reward value to update the action value function. An advantage of a TD method like SARSA over Monte Carlo is that it updates the estimates of Q at every step of the episode, aka online, making this estimate improve faster. This also allows the method to be used in continuing tasks. SARSA only requires a few arithmetic operations and a table lookup operation to update Q, so each update of this value is O of 1. Now, what if we assume that the preferred policy will always take the action that maximizes the value of the next state? This would allow us to estimate the optimal action value function directly. This is exactly what the Q-learning algorithm does. This algorithm guarantees convergence to the optimal policy as long as all state and action pairs continue to be updated. The implementation of Q-learning is essentially the same as the one for SARSA, but using the maximum action value function to update the estimate of Q. This has time complexity of O number of actions. A problem with this approach arises due to errors in the estimates of the expected value of Q. For example, if the expected value of Q for an action is negative, but due to error we estimate it to be positive, we might choose this action instead of another action that has a true positive expected value. This biases the algorithm due to the use of the same agent-environment interactions to determine both the action that maximizes Q and its estimated value. To remove this bias, we can build two independent estimates of Q, which is known as double Q-learning. We use one Q to obtain the maximizing action and the other to provide the estimate of its value. And for the implementation, at every step of the learning process, one of the estimates of Q is updated. This doesn't increase the number of computations required per time step, but since we need two estimates of Q, it doubles the memory requirements in comparison to the other algorithms discussed in this video. So far, what we have seen in this video is that all the simple reinforcement learning algorithms update an estimate of the value or action value functions. The main difference between them is that the Monte Carlo method waits until the end of the episode to make this estimate, and TD algorithms like SARSA and Q-learning make updates at every step. The way to connect these two approaches is to change how we estimate the value function. Recall that this function tries to estimate the return obtained when the agent is in a given state. The one-step TD method estimates the return using the reward obtained plus the discounted estimate of the return in the next state. We can extend that to two steps by estimating the returns considering the next two reward values and an estimate for future rewards 2 states ahead. This idea can be generalized to 3, 4, or n steps, and if your step size is as large as the episode, you recover the Monte Carlo method. This algorithm can easily be extended to SARSA by replacing the value function with action value functions and switching states to state and action pairs. In the implementation of this algorithm, the value function is not updated in the first n-1 steps of each episode, but an equal number of additional updates are made at the end of the episode, keeping the total number of dates to the value function the same. A drawback of n-step TD methods is that they require storing the previous n states and rewards, increasing the additional memory requirements from O of 1 to O of n. This is the price we need to pay to have an algorithm that often performs better than one-step TD or Monte Carlo approaches. All the algorithms we talked about so far have a forward-looking view of the learning problem. For each state visited, they look forward in time to all the future rewards and decide how to best combine them. However, we can look backwards and track the contribution of a state to the rewards obtained. As time passes, these contributions fade. This is the approach taken by the TD-lambda method. Like the previous methods we looked at, this algorithm still updates the value function using the TD error. The key difference is that each state is assigned an eligibility trace Z, which is a short-term memory vector that measures how eligible each previously visited state is to receive learning updates if a TD error occurs. When a TD error is computed, it's used to update every state that currently has a non-zero Z. This approach makes states with larger eligibility traces receive larger updates because they're considered more responsible for the current prediction error. We can use the same idea with the control problem by swapping the value function with the action value function. There are many ways to define Z, but let's look at a simple example, the accumulating eligibility traces method. The key idea behind this method is that at the beginning of each episode, the eligibility trace for every state and action pair is initialized to 0, and during each time step, the trace is updated in 2 stages. First, the trace of the current state and action pair is incremented by 1. This trace is then used to update the action value function. And lastly, the eligibility traces of all states are multiplied by a factor of gamma times lambda, causing the value of Z to gradually decay over time. The tabular implementation of TD-lambda requires us to keep track of the eligibility trace for every state and action pair, effectively requiring an additional table of the same size as Q. Consequently, the additional memory requirements is O of S times A, which can be often larger than the ON additional memory of N step TD, since N will be smaller than or equal to S. In this approach, the lambda is the trace decay parameter that determines the rates at which the trace falls. This parameter has a value between 0 and 1. Larger values allow traces to persist for longer, while smaller values make them fade more quickly. In essence, using this approach, the action value function updates are given as some mixture of multi-step predictions, interpolating between one-step updates and Monte Carlo, where lambda equals 0 gives the one-step updates and lambda equals 1 equals the Monte Carlo method. This approach generalizes the Monte Carlo for continuing tasks while also allowing for bootstrapping. This concludes our overview of the fundamental reinforcement learning algorithms. These methods form the foundation of model-free reinforcement learning and are essential for understanding more advanced techniques. Their key advantage is that they learn directly through interaction with the environment without requiring a model of the environment's dynamics. However, the tabular methods we've covered are limited to problems with discrete state and action spaces. For larger continuous problems, you need to use function approximation and policy gradient methods. But that's a topic for another video. Thanks for watching.